Okay, hi everybody. In this video, I'm going to try to quickly go through the solutions to exam 3 for ITCS-3145 spring 2023 about distributed memory. It might be a good idea to watch this video alongside your exam if you come get it, but you can certainly watch it anyway. Unfortunately, my camera will slightly obscure the questions, but you will be able to see the whole thing. Also, this copy of the exam is slightly different than the one that was given, but I don't think it substantially changed the questions. I think it just changed the wording. So you might see that discrepancy, but the questions are the same and they were evaluated the same or would have been evaluated the same. Okay, so number one, what are the main differences between shared memory and distributed memory? There are several. What I'm mostly looking at are things that you find on Canvas that look like this in our slide decks, basically pointing out that each node only has access to some partial memory. You're communicating over a network now. You've got limited memory per node. If you had 2 out of 3 of these things, generally you got full credit. But this is kind of what we're looking for. Some more details about shared memory might have helped if you distinguish it, but generally speaking, these are what we're looking for. Question 2, parallel computing is about performance. What is the main performance concern? Well, it's network communication, these sorts of ideas. We spent a long time talking about communication is a first-class issue, and it's the weakest. You might remember we drew the pyramid, kind of, where you've got compute, memory, and communication, and the farther down the pyramid, the more expensive it is, so you can draw it as a pyramid if you really want. But that's the general idea. We're just looking for communication or something that sounded like communication. Some people wrote a lot of words to tell me what communication is, and that's fine. I did my best to interpret that the way you wanted me to. Number 3, assume you have a computing cluster with a flat mesh topology network where nodes are connected bidirectionally to adjacent nodes. So real quick before we talk about this, all this is saying is you have a network. Bidirectionally means that nodes talk both ways. Right? You talk to me, I talk to you. If we were unidirectionally, then maybe you could talk, maybe A could talk to B, but B can't talk back. So that's what this is saying. Talking about the mesh topology, the way I wanted you to interpret this is as a grid, because that's often the way that the term mesh network is used in computer architecture. That's the same thing or the same deal here with describing that the nodes you're connected to adjacent nodes. So if you have several nodes, often you'll see a grid network laid out like this. And the idea is everybody is connected to their adjacent neighbors. Now, what I realized when I was grading this is that some people interpreted mesh as, or they interpreted adjacent as including the diagonal. You probably saw at first I counted off points for that, and then I decided later maybe that's fine. I don't really care. So if you drew it without the diagonals, then the answer to this question, the question is asking you what is the worst case scenario and what is the cost. For any problem where I ask you what the worst case communication scenario is, it's what is the farthest away, what has the most cost. In this case, communicating from A to, we'll just call this F. Communicating from A to F is the most expensive. If this dimension is N and this dimension is M, then it takes you N to get across and M to get down. So L times N plus M is the answer if you didn't put this, but you put some variation of this. If you put times M, you lost some points because that's not the math, but you did get generally the right idea. If you included diagonals, then it won't be the Manhattan distance anymore. It will just be the like the L2 norm or the Pythagorean theorem, basically. m is the square root of m divided by n. If you put, or sorry, m squared times n squared. If you put that, you got credit. There's no log or anything involved in this. You might remember seeing answers like this. Log base 2 generally has to do with binary trees. Binary meaning 2, 2, right? Binary. So binary trees are different. We did have some test problems. We've talked about binary trees in a lot of different contexts. They're used for a lot of different problem solving. They're a useful abstraction. In general, the length from top to bottom of any branch of a binary tree is log n. That's what you're thinking of. It doesn't have anything to do with topologies inherently. It has to do with, this is a property of a binary tree. Okay, so then the next question is about the Mandelbrot set. So each question here, give me one second. Okay, so the question here is asking you about the Mandelbrot set. We've split it up into 4 chunks: processor 0, 1, 2, 3. Black dots require more computation, and white dots don't require a lot. This computation is kind of interesting. If you actually look it up, it uses complex numbers. It's a fractal, so you can, if you were to compute this live, you could zoom in as far as you wanted. It continues to grow. It's a very cool problem. For this problem, did you think it was efficiently partitioned? The answer is no. It's not. Most people got this generally pointing out that P0 and P2 have much less, have a much smaller region of actual computation. Remember, the darker regions are where the computation happens. So these regions, this tiny circle or this tiny blob is clearly much smaller than this blob. That means you have bad load imbalance. If you wrote no comma load imbalance, then you got full credit or any variation of that. Number 5, you're given a code base. So this question, so let's read it first. You are given a code base that contains a sequential implementation. You're asked to measure the performance of the code and then use Amdahl's law to predict the speed up if you were to parallelize it with MPI. So basically, you're given sequential code. You're supposed to take some measurements and then make some predictions about how long it will take. This is asking you how to do a benchmark. You've been benchmarking all semester. We've talked about performance a lot. So this is just asking you to think a little bit about how that process happens. So for A, explain how you would implement this so that you can do Amdahl's law. Well, if you think about Amdahl's law really requires 2 pieces. You have for any given code, if your code looks like this, these are lines of code, you have some lines of code that are part of your parallel region, or they're pieces that you think can be parallelized. And then you have pieces that are sequential that you cannot parallelize. You've done this in your programs that you've written. You've had chunks that cannot be parallelized. You have chunks that can be. The question here is basically saying, where do you put the timers? Well, what we're looking for is you need to put timers around the parallel region. So clock. There's several ways you can do this depending on what you wanted. I would have accepted any variation. One possibility is you set a timer up here, you set a timer down here. Let's say A, B, C, D equals. And then what you do at the end is you do B minus A is your total, and D minus C is your parallel. So you could subtract total minus parallel to find the sequential. Equally valid is you could have just timed each sequential region, and of course you didn't have to write it like this. If you just described what you did, you got full credit. We're saying you need to separate. Amdahl's law requires a sequential and a parallel component, so we need to find both. Now, again, we're starting with a sequential implementation. We're starting with a sequential implementation. If we're starting with a sequential implementation, that means that you don't have anything that is parallel yet. You're going to time the pieces that you plan to make parallel. And a lot of people got this. But some people just suggested, well, we time the beginning, we time the end. But that assumes you have no sequential region, which isn't quite there. So you probably got half points for that, which is 2 because it's only part A. Part B is why. Why do we measure again once you do parallelize it? Doesn't Amdahl's law tell us how fast it's supposed to be? And most people did get this, even if they didn't get A. Basically, we need to time it to see what the difference is. Amdahl's law is an upper bound for performance. We need to know what our actual performance is. Maybe it's not as high as we expected. Maybe there's overhead, bottlenecks. Maybe we didn't do it right. Anything like this got full credit. Even if it didn't capture the whole idea, I was pretty generous on giving credit for this one if you told me a reason, a good reason to do it. Number 8, what is wrong with this program? So this is main. Again, this is a complete MPI program. This is main. We call MPI com size before we call init. That's a mistake. We return from main without calling finalize. That's a second mistake. Most people got this. Some people only put one or the other, which surprised me. If you looked for one, I think you'd look for the other, but that's what it was. Didn't really have anything wrong with these. These match. You've got one value that you're sending. You've got you're sending to node 1, you're receiving from node 0, you're sending to node 0, you're receiving from node 1, that's all fine. This is basically the more or less correct code for the ping pong, or at least to some variant of the ping pong assignment that we did as homework. Number 7, assuming the code is executed correctly, what's this code output? If not rank, or otherwise, what that means is if rank equals 0, not in C, not anything positive or negative. So not 5 is 0, not 7 is 0. Not 0 is 1. Basically, not anything but 0 is 0, and not 0 is anything but 0. So point being here is if your rank is 0, then you execute this piece. If your rank is anything else, you execute the other piece. If you run this with 2 processes, then you print pong. There's actually a slight bug in this where this is missing a null terminator, but whatever. You print pong, and then you send this entire data. You send 4 characters to the other process. Then you print pong again. Change the value of I. So you change value 1. You change the O to be I. Then you send the characters back, so you send the whole thing back. So now it's pinged on both processes, and then you print ping. So the output is pong, pong, ping. Some people didn't show the output. It asks you for the output. Some people didn't show me the output and described this so vaguely, I couldn't figure out what they think this program does. Generally speaking, if you wrote the output, you got full credit for this, but that's not going to happen in the future. you need to tell me what the program does. Likewise, if you only count the last printf, that's not enough. There's other output. These printfs could have printed something else. That's what I'm looking for. I want to know when you think these things happen. Okay. Two functions generally do the same work, same outcomes. This is not a C test, and some of the answers I got about C are kind of hand-wavy anyway. It doesn't really have anything to do with malloc and free specifically. That's not a big deal. This is a distributed memory test. I'm asking you, is sending inside the loop better or is sending outside the loop better? Sending outside the loop is better. Why? If we come here to our slides, we find that the large I/O is typically faster. You want to do single bursts of I/O. We spent a while talking about this. You want to do, actually, I think we talked about this more than once. We did a single I/O, and that's fine. So number 9, illustrate. Oh yeah, so the answer here is bar. Bar is faster. Generally, if you measure them, it'll depend a little bit, but bar intuitively is faster, which is what this is asking about. In practice, that's probably true. Number 9, illustrate how the process memory table changes. Well, we'll actually just take a look at the slides real quick. So if you take a look at the slides that show this representation of memory, gather will turn ABCD into ABCD across. It'll turn a column into a row, or rather, it will take data from every process and turn it into one large data chunk for a single process, whatever the root process is. But this question is asking you about all gather. All gather, again, all prefix sends the result, it broadcasts the result to every process. So it's the same as a normal gather. It's the same as the gather up here, ABCD. The column turns into the row, but it broadcasts the result to everybody. If you did gather, you got half credit. If you wrote something else, you got what I thought showed me your best understanding of what's going on. Okay. Number 10. So what are the advantages and disadvantages of asynchronous MPI? Something I want to point out here is asynchronous. Asynchronous means something very specific. I think everyone who caught the word asynchronous understood what we meant and tended to get full credit for this situation, at least for advantages. What are the advantages of asynchronous? Well, the advantage is you call send, you block. If you call isend, the asynchronous version, you keep computing. You can overlap the communication. At the end of this video, I'll go through and show you where the resources are for all of these things. We talked about all of this in class, but I'll show you where they are online too, on Canvas or other. So isend will let you keep computing. You don't have to wait on the other process. The disadvantage is there's overhead. It's complicated to do this. I got some answers about deadlock. It can eliminate some types of deadlock, but it really just pushes the issue further down the road. You can still deadlock, but it's a little more tricky. Depending on how well you explained it, I generally gave you full credit or something very close to full credit if you put deadlock or one other singular reason for any of this. 11, describe how you would use MPI collectives, keyword bold. To partition an equal number of rows in an n by n matrix to every MPI rank, you can add or define variables. Adding or defining variables, some people went a little crazy with. Generally, what I was looking for is if you wrote something along the lines of MPI scatter, this will get you full credit because that's all you have to do. MPI scatter partitions data. we can take a look at the example. MPI scatter partitions this data into equal size chunk and sends it to each process. That's what scatter does. So real quick, and then number 12, this question, the biggest killer for people was just leaving it blank. Now, only some people left it blank. A lot of people got at least half credit. There are cases where I couldn't really tell what was going on and I didn't really give a lot of partial credit, but if you wrote something in the direction you got half credit, then generally you worked your way up. What is this question asking? Well, it's asking you implement bcast broadcast. Implement broadcast, the collective, using only point-to-point communication. So broadcast is like any other problem. In fact, it's a problem you should be more familiar with. You just want to basically, what broadcast does is you take the data of one node and you send it to every other node. So to write code that does this, you need code that will send data to every other node if you're the root. If you're not the root, you need to receive data. And that's the part that tripped up a lot of people. And you still got something like 3/4 credit if you didn't catch that. But basically this receiving part is what caught people. So I will pseudocode this real quick. Basically, you get the normal bcast arguments. I removed the typing to save you some writing. But you get some arguments including root and a buffer that I'll just call B for right now. Basically, if rank, and so some people pointed out that you should call MPI com rank, and that's fine. Some people called MPI init. I didn't count off for that, but you've already called MPI init by the time you call broadcast. You don't need to do that. In fact, calling it twice is probably going to break something. MPI com rank to get the size, and then once you have a size, to get the rank, once you have the rank, you can say if rank is equal to root. If rank is equal to root, you're the sender. So for I less than size, again, if you didn't include these, I didn't count off, but you should have done the same thing for size. If for I less than size, if I does not equal rank, this is actually important. If you didn't do this, I didn't count off because I know this is an exam and you kind of get the idea. But it's important to make sure you don't, otherwise you will deadlock trying to send data to yourself. Again, I didn't count off points for that, but if you were to do this, that's important. If I doesn't equal rank, then send to, basically you send B to I, and you fill in all the parameters that you had up here. You need to send the full data to everybody, these sorts of things. But if you wrote something like this, I generally gave you full credit because you showed me you know what you're doing. And that's the idea, is you loop through every other rank and you send them the data. Now, often, I don't think I got any answer that looked just like this. I got things that looked kind of close to this. And then the question is, well, okay, but the receivers call MPI bcast too. So you need an else. And if you else, you receive. And if you wrote anything that looks remotely like this, and actually even if you didn't include this if statement, like I said before, you got full credit. It's a problem you have to think through, but you know how bcast works, and you know how sending data works, and we've discussed MPI broadcast in the context of, well, you do MPI send to everybody. We actually walked through this problem in class, I think on Friday the 28th, or maybe the Wednesday. But we did walk through this in class and do basically the same sketch. I understand it can be interesting because you're implementing MPI with MPI, but that's how abstraction works. And I think this is a problem you should almost be more comfortable with than if I'd given you how do you use MPI point-to-point operations to solve an in-body simulation. I think that would have been a lot more confusing. Again, people that got in the right direction got points. Even things as little as pointing out you need to send and receive. Of course, just writing send and just writing receive is not enough. You'll deadlock. But you still got points in that direction if you wrote something. Okay, so that's the end of the exam. Very quickly, we can go through the questions and I'll point out the resources. So number 1, what are the differences? Well, if you go to the first slide deck, Intro to Distributed Memory, you will find a list of differences. Number 2, it's about performance. What is the main concern? In the slide deck, this one or the adjacent one, the follow-up one. Let's see real quick. Let me just pause real quick while I find it. Okay, I paused to find it, and it's right here. Minimizing communication is primary problem. On this question, I forgot to mention, sometimes I did get some things about load balance and things, and usually did get credit, but we've talked about communication as the most important thing, including the pyramid. Communication, memory, compute. Communication is the most expensive. It's the primary. Load balance stems from these kinds of problems, how you distribute. Load balance is a problem with the way that you communicate. You're sending too much data to single nodes to solve too many problems. Another portion doesn't actually get as much work. Okay. Question 3. So assume, so the mesh topology. So in the topology example, like I said, it was described as a grid, which is why I interpreted your mesh question fairly. Whatever definition of mesh you used, as long as it basically had adjacent nodes as contiguous, I took and accepted. You'll often find mesh topologies described as things like this, which is what we're getting at. I could have used the word grid, but the idea is the same. Anything where you've got adjacent nodes that are connected to all of the other adjacent nodes. Okay, so number 4, the Mandelbrot set. So this is a partitioning question. And we discussed this in context. I'm not going to spend a ton of time on it, but the idea is the same here. Some quadrants have too many things to do. Other quadrants don't have enough. Workload imbalance. So we talked about this a lot when we talked about it in class. Okay, next question. Number 5, Amdahl's law. So this is a question, again, if you know Amdahl's law, if you know that you need a parallel and sequential point, then this is that's step 1. Step 2 is you've seen programs that benchmark code. Now they've only so far timed the parallel region. This question is asking you to think, well, what do you need to have both pieces of Amdahl's law? Sequential and parallel. So by now we're asking you to think, how do I apply this? Number 6, below is a complete MPI program. So this is your ping pong. I don't think, well, there is a ping pong example. The ping pong example is in the slides. For one of the point-to-point examples, I forget which one. I guess it was probably the second one we discussed point-to-point. Loosely this, ping pong. So you've seen the pseudocode. You should have implemented the code yourself or come to office hours. That's generally what this is getting at. Now that being said, MPI init and MPI finalize. Well, we did have an MPI introductory slide that we discussed. You need init and finalize. And if you did your assignments, you either did init and finalize or you crashed your program and then figured out you needed to do it. Okay, next question is number 7. The same problem as the ping pong, actually. Most people got this if they got the previous question. It didn't really trick anybody. It's not really meant to be a trick question, but the idea is you send the data, you receive the data. Back and forth, the data is a little changed at the end. Number 8, the following two functions perform the same work and have the same outcomes. Which one's more efficient? This goes way back to this first slide deck. Again, we spent time talking about the communication, and we spent a good amount of time talking about, well, you send larger messages, you do better. Sending repeated sends is bad. And a lot of people probably didn't even remember this. I got answers like, you're going to have to receive a lot more. And that's true. That's where some of the overhead comes from. The rest of the overhead comes from packet and network handshaking and all of these sorts of things. We didn't dig in too much to the symptoms, but if you wrote anything remotely like that, you got credit. Number 9, well, I just showed you in the collective slides, number 2. It's pulled straight from the example. You should know how the collectives work. What are the advantages and disadvantages of asynchronous? Well, point-to-point 2, we talked about asynchronous a lot. We talked about problems you can solve. We went through this example, which is really asking you what the question is. By the way, here's our mesh exchange as a callback to number 3, although again, I did interpret that friendly to you if you assumed you had diagonals. I assume this is where people got the deadlock concept, but yeah, you still got kind of credit for that if you do it. But anyway, generally, this is where we talked about asynchronous, and we talked about overhead and these sorts of things. Again, so the disadvantages of asynchronous were weighted. So advantages were 6 points, disadvantages were 2 points. How would you do this? This is your homework number 6. At least you would have done this specific problem in homework number 6. But the key words here are partition equally. You don't send the same data to everybody. The most common mistake I got here was to put broadcast. Broadcast does not partition. Broadcast sends the same data to everybody. Likewise, some people tried to do this with send, almost like we did for number 12, asking you about MPI collectives. This is a question about MPI collectives. You only need one line of code. And then finally, the bcast. Again, if you know how point-to-point works and you know how bcast works, you can refer to the bcast block here. This is the hint on the implementation. You do A from process 0, you send it to everybody else. If root is a different process, you send it from a different process. But generally, you send to everybody. Everybody who's receiving data has to receive the data. That's fundamentally how MPI works. Whether you're doing collectives or point-to-point, it's the same thing. Okay, so that's the entire video. The grades should, if you're watching this, the grades are probably out or will be out shortly. I think in this video we pretty much covered everything. We went over the exam, we went over how it was graded, and we went over why it was graded, what the common mistakes are, and also what the resources are to answer these questions. Again, it all comes from the slides and the content we discuss in class. So yeah, don't forget on Wednesday we have a study session. If you have questions, you should come and ask them, and we'll talk about whatever you want, including these topics. Yep, otherwise we'll see you next time.